Okay, yeah, now it's recording, right? Okay, good. So yeah, this is the probability density function for the normal distribution. And then there are two parameters. One is the mean and the other one is sigma squared. So last time we showed that the mean and the variance are equal to that. That's a known result to you, but we're just showing the procedure on how to deriving them. And today we are going to continue our discussion on things related to normal distribution. Okay, yeah, so we write x follow a normal distribution, and then the x is ranging from negative infinity to positive infinity, which is the support. And then for the mu, it's just a real value scalar. And then for the sigma square, or sigma, it's also a real value, but it has to be positive. Yeah, so that would be the setup for the normal distribution. And then we also have a special case, which is called the standard normal, where when mu is equal to 0 and then the sigma square is equal to 1. Okay, so then immediately we know that the probability density function for a standard normal distribution will look like something like this. So that the sigma square, you just say 1, so it disappears, and then you minus a 0 over a 1, so that it only becomes a z squared here. Okay, so now we are going to talk about the moment-generating function for the normal distribution. So we are going to start. Okay, yeah. So last time also someone pointed out that if I can give like a clear like a notation regarding the quantity that we are calculating. So whenever I write like a examples, it's just referring to I'm like starting like calculating, or you can consider this as like a homework question, and then we're calculating something, and then we want to get the answer of something. Yeah. So just to make sure that notation is clear. Okay, so this is the quantity that we want to calculate, which is the moment-generating function for the standard normal random variable. So this is referring to this probability density, which is the z following the normal with mean 0 and 1. Okay. And this is the quantity that we want to calculate. So anyone still remember what is the definition for the moment-generating function? Which is just the expected value for e raised to the power of tz, right? Our random variable is z here. Okay. So what we want is to evaluate this expected value, which is the integral, and then e raised to the power of tz, and then copy down the probability density function. So 1 over square root of 2 pi, and then exp negative 1/2 z squared, and then dz. So we're just calculating or evaluating this expected value for this function. Okay. Next, we are going to simplify this expression inside the integral. So again, for the upper bound and lower bound for the random variable z, and we are going to group the exponential term from this function and from the density function together. So what we will have is 1 over square root of 2 pi, and then exponential of negative 1/2 z squared, and then plus tz. Okay. So any thoughts on how to simplify this expression here, or how to work on this integral? Okay, so what we are going to do is that we are going to complete the square for this expression to make it something like a, or let's say a minus b square. So we're going to insert some component inside the parenthesis to make the terms look like something like that by construction. So that will be our strategy here. Okay, so we are going to insert a value in the following way. Any thoughts on what are the terms we should insert here to make that to make it look like that? To have a square term. So we can minus a 1/2 t squared and then add it back, so that the quantity is not changed. So we just add and minus the same thing. And then here, the things that are underlined will become some square term here. And then this one here, it just acts as a constant. So you can always move it outside and even move it outside the integral. So what we have is the following. So let's first complete the square. Okay, so maybe I put the 1/2, I bring this constant outside first. And then inside the square bracket, you will have z squared minus 2tz and then plus a t squared. And then you have another copy of 1/2 t squared dz. Okay. And then let's say we first bring this component outside the integral. So what we have here is e of a plus b, and then we want to rewrite it as ea multiplied by eb. And then here we let the b equal to 1/2 t squared. Because it does not involving the random variable z here, it serves as a constant, the e raised to the power of b, so that we can move it outside. So what I mean is that we can write e raised to the power of 1/2 t squared. From here, move it outside the integral. And then we have the following inside the integral. So I think it's z minus a t squared and then dz. Okay, so now what do you think about this integral here? Any thoughts on what this integral should equal to? Or what does this expression represent? So is this the density function for a random variable z that follow a normal distribution with mean mu equal to t and then the variance equal to 1? Is that the case? So if this is a density function, and then when we a normal density function, and then we evaluate to the integral from negative infinity to positive infinity, then this will just reduce to e to the 1/2 t squared and multiply by 1. Right? So this is the moment generating function for a standard normal random variable. Any question or comments? Yeah. Sure. Yeah. So can I put it here in the front, or like a moment? Like you mean in text or symbol? Because this is just this. Okay. Sure. Like MGF for or random variable z, or okay. So not to confuse with this z here, that follow a normal 0, 1. Is that okay for if I just write that like something like that in the later on, or for the, is that okay? Okay, yeah. So this will be the moment generating function for z, and this is for z following standard normal. Yeah. Okay, yeah. Thanks for the feedback. Yeah. Any other question or comments or feedback? And also, I just pointed out that I usually put the examples in the front. So this is also the quantity that we evaluate. So you can always consider this as like a exam question or homework question. So if you want, you can also like starting from here, the first line, and then do it on your own to complete the rest and see if you get the result from this notes. Yeah. Okay. Any other comments or question? Okay. If not, then let's start another, let's say, examples. So now, let's say we have a random variable x that follow a normal distribution with a general mean and then the sigma square. So our goal for this example is to find the moment generating function for this random variable x. Yeah. So we will be evaluating this expression now. So any thoughts on how can we, using a simpler way to calculate this expression without doing the integral as what we did for a standard normal distribution? Any thoughts? Given that we know the moment generating function for a standard normal look like this, any thoughts on how to, using a simpler version or a way to calculate this moment generating function? So one thing you can do is to consider this x as a transformation from a standard normal random variable, which is what we showed from last on Tuesday. You can write the x in terms of sigma multiplied by z for z follow a standard normal distribution. So this is a transformation that we mentioned last time. And then now we can write this as a sum from mu and then sigma square and then multiply by z by consider this moment generating function, or by transferring the moment generating function with respect to x to a moment generating function with respect to the random variable z. And then because we have a z, the moment generating function for z already, so we can use some knowledge from here to simplify our calculation here. So that will be our strategy here. So anyone still remember what are the properties for the moment generating function when we have some functions of a random variable? So what I'm referring is that for Munch function of, let's say, a plus bx, one of the property that we show, I think, from last week. Anyone still remember what does this equal to? Okay, so in the formula that we provided before, this is equal to e raised to the power of at multiplied by the momentary function for the random variable x, and then with the t, change it to bt. Do you still remember, or does this still like remember seeing something like that? Okay, good. So this property for the momentary function is what we are going to use for here. Okay, so now we just need to match what is a and what is b to this expression. So let's see, we have e and then raised to the power of a multiplied by t. So a in our case is the mu here, and then plus b and then z. So our random variable is the z here. So sigma will serve as the b and mu will serve as the a from here. So all we need is just plug in, all we need to do now is just to replace the terms for the parameters of a normal distribution. So we will have e raised to the power of at, and that means we have e raised to the power of mu multiplied by t. And then multiplied by the momentary function with respect to the random variable z, and then for t equal to b multiplied by t. That's that. Let me also use the sigma for b. Does that make sense? Okay, so now we just need to further substitute the momentary function for z with this expression that we get earlier. Okay, so now we have e raised to the power of mu t multiplied by e raised to the power of 1/2 and then t squared, except that our t here is sigma t, and then altogether taking the square. And now we can simplify the expression as e raised to the power of mu multiplied by t plus 1/2 sigma square t square. And this also, let me write it down, is the moment generating function of random variable x for x that follow a normal distribution with mean mu and sigma square. So just to make a mention the differences is that this one here is the moment generating function for a standard normal random variable, and this expression here is the moment generating function for a random variable x that follow a general normal distribution. Okay. Any question or comments? Once we have that, we can talk about some other questions, such as what is the distribution for some functions of random variables. Okay, so now let's start with another example, and then here is the question. So let a random variable x that follow a normal distribution with mean mu, and then here we use a subscript 1 to distinguish the random variable for, that we are going to use later, or some other random variable. So let's first, for the random variable x, we have the parameter mu1 and sigma1 squared. This is the parameter for random variable x. And then let's say we have another random variable y that follow a normal distribution with mean mu2 and then sigma 2 squared. And then we also have the condition that x, y are independent. So now our question is, what is the distribution of our new random variable that is specified by x plus y? So any thoughts on how to find the distribution, or how to conclude what is the distribution for x plus y here? Y is a plus. Okay. I think if they are independent, it should be the product of the two momentary function, right? Yeah. Yeah. So the yeah. But the bottom line is that we want to use the momentary function to show, or to at least to see what is the momentary function for this new random variable x plus y. Yeah. And then here, let me write down, because they are independent, we will have the momentary function for x multiplied by the momentary function for y. And then for x is following a normal with these parameter, and for y is the momentary random variable normal random variable with these two parameters. So now we can just copy what we get earlier for the momentary function. So can someone read what we get from our last exercise? What is the momentary function? The one, if you just write down. So what I'm referring is mu1 multiplied by t, right? And then 1/2 sigma 1 square, and then t. Let me use t now. Okay, t squared. So now I'm just simply copying the momentary function from above here, the one that we get from here. Yeah, but just don't forget that we have a subscript mu1 and sigma 1 to distinguish between random variable x and random variable y. So copy down the momentary function, but make sure you don't forget there's a subscript here. And this is the momentary function for x only. Okay. And then we need to also write down the momentary function for random variable y, and which is mu2 multiplied by t plus 1/2 sigma 2 square, and then t square. Okay. And then we can combine the two products. So we will have e raised to the power of mu1 plus mu2 multiplied by t, and then plus 1/2, let's see, then I put sigma 1 square, and then plus sigma 2 square together, and then t square. So this is the moment generating function. Let me write it down in text then. The moment generating function of x plus y. Okay, so now the question is, by looking at this expression here, what can we conclude about the distribution for x plus y? Does this expression look like something that we have seen? So isn't this just the moment-generated function for a normal distribution, right? Except that we have a different parameter here. So first of all, we can conclude this is a normal distribution because the moment-generated function, the resulting moment-generated function, looks the same as the moment-generated function for a normal random variable. So now the question is, what are the parameters? So by reading from this expression, what is the new mean value here? It should be mu1 plus mu2, right? For this part is referring to the mean value, right? And then what about the variance term? What is the variance by reading from this expression? It's just sigma 1 square plus sigma 2 square, right? So this will be our conclusion for this, let's say, example or question. So what is the distribution for x plus y? Is a normal distribution with mean value equal to mu1 plus mu2, and then sigma, the variance sigma 1 square plus sigma 2 square. Okay. Any question or comments? So just one more comments regarding this, so that the sum of a two normal distribution will have the variance equal the variance equal to the sum of the individual variance only when x and y are independent. So if they are not independent, then don't forget there's a covariance term for the x plus y. But because they are independent, this term goes to 0. So not every time the sum of two random variables will have that case. So just want to point out that just be careful. If missing a keywords, the result can go very different. But in this case, we have x, y, they are independent, so that we have this result here. Okay, just want to point it out for that comments. Okay, then let's start at another example. So what we have done is that we sum two random variables together. So now what about we sum over, let's say, n copies of the random variables. So let's say we have x1 all the way to xn. And then now we use the keyword IID. And then for each of them, they follow the distribution with mean, mu, and then sigma squared. So now the question is, what is the distribution of t, where t is x1 plus all the way to xn? So any thoughts on how we find the distribution for t? Yeah, so again, using the moment-generated function. Yeah. So the moment-generated function for our variable of interest, which is t here, the capital T. And this is just the sum for x1 to xn. And then here we are going to use the keywords independent m of x1, and then multiply all the way to the moment-generated function for xn for xn, yeah. And then let's write it down. So the momentary function should be mu t plus 1/2 sigma square t square. Okay, so that is for one of the random variables. And now we are going to use the second keyword, which is identically distributed. So maybe I just put identical here. And then because all of them, or each of them, they all have the same formulation for the momentary function, so that the product of them is just this expression raised to the power of n. And then to simplify this, we just have e raised to the power of n times mu times t plus 1/2 n times sigma square times t square. So that is the moment generating function for t. So any conclusion that we can derive from here regarding the distribution for t? It should still be a normal distribution, right? Because it has the same formulation of the normal, momentary function of a normal. So the question will be, what is the new mean value and the sigma square here? Yeah, so the mean value should be n copies of mu's. This is like we have mu1 plus mu2 and all the way to mu n. So there are n copies of mu, because each of them, the mu1 and all the way to mu n, they're all equal to mu. That's what the identically distributed mean. Yeah. And what about the sigma, or the variance here? Yes, so n copies of n sigma squares. And again, this is because all the x1 to xn, they are independent. Okay. Any question or comments? Okay, then let's do one more examples which related to this quantity here. So let's say again x1 to xn, they still are having the same setting here. They all follow identically or independent distributed with this normal distribution. So now the question is not the distribution for t, it's the distribution for x bar, where x bar is 1 over n summation for xi. Or you can write it as 1 over n multiplied by t. So is there any simpler way, or how can we evaluate the moment generating function for x bar, which is just a coefficient multiplied in front of the random variable t? So anything we can use from the properties to simplify this expression? So what I'm referring is that when you have a moment, when you have a moment generating function for ax, this is equal to, let me check the formula. Okay, so this is equal to the momentary function for x, but t is equal to at. So this is the property that we are going to use. Okay, so in terms of the random variable t, so what we have is the momentary function for 1 over n multiplied by capital T. And this should be equal to the momentary function for capital T, but 1 over n multiplied by the lowercase t. And then we can just copy the moment function for random variable capital T, which is what we get here. So let's write down e raised to the power of n multiplied by mu. And here, the t is different. So the t is 1 over n multiplied by t. So let me use a parenthesis to make it to distinguish between this and this expression. And then also for the 1/2, n multiplied by sigma square multiplied by 1 over n multiplied by t, and then all together taking the square. Because this time the t is different. So then to simplify that, we have the n cancel out from the first term. So we only have mu multiplied by t. And what about the second term here? So we have one copy of n here, but we have 2 copies of n in the denominator. So that means we have a 1 over n sigma square and then t squared, right? So now what can we conclude about the distribution for x bar? Sigma square over n, right? Yeah. So the distribution for x bar, first of all, is normal by reading this expression or recognizing this expression with the moment function. And then the mean and the sigma variance, you can just read from here. So the mean is the mu, and then the variance is 1 over sigma square over n. Okay. So just to conclude our discussion for this momentary function of functions of normal random variables, maybe let me use one more expression, one more, let's say, way to calculate the 2 terms here. So what we want is essentially the expected value for x bar and the variance for x bar, right? This is the expected value and this is the variance for the new random variable, which we call x bar. So another way you can do it is that you can simplify from the expected value and the variance definition. Yeah. So now let's replace the x bar with 1 over n summation xi. And then 1 over n is a constant. And then we just have the expected value for x1 plus all the way to xn. And then we can distribute because the expected value is a linear operation, so that we can distribute the expected value to each of the terms here. So essentially we have 1 over n e of x1 plus e of x2 plus e of xn. And now, what is the expected value for each of the random variable x? So we can just look at the question. What is the expected value for each of the x? Which is just the mu, right? Yeah. So then this expression you have is just 1 over n, and then you have n copies of mu, because each of them has a mean value or expected value equal to mu, and then you have n copies of them, and this will give you the mean value here. So you will know the expected value is equal to mu. And what about the variance for x bar? We can also write the x bar as 1 over n summation xi here. So when we move the constant outside the variance, what do we need to do here? We have to take the square, right? So 1 over n squared. And then we have the variance of the summation xi. So how do we express the summation, the variance of summation here? So is there anything we should concern about it before we, let's say, expanding the term? We need to know whether x1 to xn are independent or not. So in our case, it is independent. So then we have the following result. But if they are not independent, then you need to consider, let's say, variance of x plus y for 2 random variable cases. You will have variance of x plus variance of y, and then you will have 2 times the covariance of x plus y, x and y. But in our case, this is independent, so this will go to 0. And then for more variables, you will need to consider the covariance between each pair of them. Yeah. But just in our case, because we have the independency here, all of the covariance go to 0. So we don't need to worry about that. But in general, you need to tell yourself always to see whether they're independent or not, or to calculate the variance or not. Yeah. But in our case, we don't need to worry about that. So then back to our expression, we have 1 over n squared, and then let me use square bracket. So variance of x1 plus variance of xn. And this is only when they are independent. Okay, so let's continue our expression here. 1 over n squared. So what is the variance for each of the random variable xi here? It should just be the sigma square, right? Because each of xi follow normal, mean, mu, and sigma square, right? So then this summation here will give us n copies of sigma square. And then to simplify that, you will have sigma square over n as what we get from using the moment gradient function. So we will have this quantity also calculated. But what we don't know from this method is what is the distribution here. So if you want to know the distribution, the normal distribution here, you have to go through the moment gradient function. This expression, by calculating the expected value and the variance, will only give you these 2 terms. But to get the normal distribution here, you need to go through the moment gradient function again to know that this is a normal distribution. So make sure that evaluating the mean value and the variance does not tell you what is the distribution underlying the random variable. So you have to go through the moment gradient function, or you can either deriving the density function to know what is the distribution here, the normal here. Does that make sense? Okay, just comments regarding the things, or to conclude this question here. Okay, any question or comments? Okay, if there's no other question, then I'm going to talk about something new here. So today we are going to talk about a thing called method of transformation. So this is another thing that, or you can say a statistical tools that people use in, let's say in statistics. Yeah. Okay. So first of all, we are going to talk about the one variable case, or a unit variable way, the method of transformation for a single random variable. So now, the main, let's say, the procedure is can be stated in the following way. So let's say x is a random variable, and then we have a function that's called y. It's a function of the random variable x, and then if the function, okay, then let me use g then. Okay, if this function g for the random variable x is either an increasing function, or decreasing function. So increasing and decreasing function just mean like, for example, they just keep going up, like increasing, or they keep decreasing. Not something like decrease first and then increase first, and then increase afterward. Not something like that. So if your function satisfies that it is either an increasing function or a decreasing function, then we have the following result, or more specifically, the probability density function for your random variable y, the one that is a transformation for your original random variable x, has the following expression, which is the density function for your random variable x, but you need to input the expression. So here, let me use a different notation. So h inverse, which is the inverse function for the function g. And here, you need to input the variable y. So later, I will talk more about this. So here, I'm just presenting the result here. So you need to plug in the inverse function for the g inside the density function for random variable x, and then you need to multiply another value, and the other value is the derivative for the inverse function with respect to the variable, the new variable y here, and then you need to take the absolute value. So when you plug in all the component, or to calculate all the component here, you will get the density function for your new random variable y. So that is the result for the transformation. So now I'm going to talk more about this function h, or h inverse. So the y is equal to a transformation of x via the function g. And then x is just the inverse function when you input the variable y. So the only difference is that when you input the random or input x, and then the function g will give you the y. And when you put the input when you have the input y to the inverse function of the g, you will get the output x. So you input g, you get y, and here you input y, you get g. You get x. Yeah. So that's the two things. Yeah. Okay. So now we are going to do an examples by using this method of transformation. So let me put example. So now suppose the random variable x following a gamma distribution with parameter alpha, beta. And then you have another variable of interest that's called y, and then it's a function of this random variable x. And this function has the form of c, a constant c, multiplied by x. So that it satisfies our condition as an increasing or decreasing function. Depends on either the sign for c. Is there any question or anything? Sorry? Which one? This one? Right after alpha, beta? Oh yes, y, sorry, yeah. Yeah, no problem, just let me know. I know sometimes my handwriting is very, no one can recognize my handwriting, yeah. So yeah, just let me know anytime, yeah. So it's a y equal to g of x. And then, a question? Sorry, can you say that again? Oh, just an arbitrary function. Let's say we're just interested in this function for just like a constant multiplied by a random variable. Yeah. So this is like an arbitrary. It depends on based on your own. Now, for example, you can also write this as like 1 over n summation xi. Let's say people interested in x bar, then the c can be 1 over n, and then the x can be like summation of x, something like that. Yeah, just if someone interested in the mean value. But let's say here we're just interested in c multiplied by x, like an arbitrary function. Yeah, good question. So let's say the g of x has this particular expression, and our goal is to find the density function of, maybe let me put it here. So what we want is that the density function for random variable y, because we know the density function for x for a gamma distribution, but let's say it's a transformation of a random variable, and we are interested in this. How can we solve for that? And then we can use this expression here to get the density function for random variable y. So maybe first we can talk about the transformation. So y is equal to g of x, which is equal to c multiplied by x. So what is the inverse function here? That you should input a y that gives you an x. So what should be the expression for h inverse y? When you input a y, you will get x in return. Or another way you can think about this is just like you can moving the c, or think about a way to get x on one side. So essentially you will have 1 over c multiplied by y, right? So y is equal to c multiplied by x, and then x is just 1 over c multiplied by y. So you can think about like putting the x on one side, what will happen on the other side. So that the inverse function, the expression, will have 1 over c multiplied by y. So then we have the bridge between x and y here. Okay, so now we just need to calculate or plug in all the components here. So we have the h inverse y figured out. Now we need the derivative. Okay, so we want, let me put it here, d of h inverse y. It's a function of y here. And then dy, which is just a dy for 1 over c multiplied by y. So what does this equal to? Just 1 over c, right? Okay, so maybe let me give one more constraint here for c greater than 0. If I don't put c greater than 0, when you take the absolute value, you will need to consider whether the c is positive or negative. So you need to discuss case by case. But here, just for simplification, let me also add c greater than 0. So that the absolute value for 1 over c is still going to be 1 over c, right? Okay, so just let me add in one more constraint here. But without this constraint, you need to consider when c less than 0, when c greater than 0, when you talk about the absolute value. Okay, so now back to our expression for random variable y. And then this is equal to the density function for random variable x, which is the gamma distribution. So maybe just to remind you what is the gamma density function, let me put it here. So f of x is equal to x raised to the power of alpha minus 1, and then e raised to the power of negative x over beta, and then a gamma function, and then a beta alpha. So that is the density function for random variable x, which is the gamma random variable. But what we want is the f of y, the new random variable of interest. And this is equal to the f of, so I'm just not going to copy down the formula here, which is the f of x, but you need to input the inverse function here. I'm just going to write down the result directly. So for the x, you need to replace by the inverse function, so which is 1 over c multiplied by y. So this is your new input. So here, this is your new input to the density function for random variable x. So you just need to replace the input x by 1 over c multiplied by y, and then raise to the power of alpha minus 1. And then you also have e for negative. So x here, again, your input to this function is going to be 1 over c multiplied by y. So you need to replace x by 1 over c multiplied by y. So that will give us y over c multiplied by beta, right? If you plug in 1 over c multiplied by y for x, for input. Okay, so that's the numerator. And then for the denominator, there's no more x, so you can just copy from the normalizing constant. Okay, So that's the first part. And then don't forget you have a absolute value for 1 over c. But it's just going to be 1 over c for c greater than 0, which we assume here for now c greater than 0. So you have to multiply by that. Okay, so now we just need to, also I just want to point out this is a function of y. So you will see that there's no more x showing up anymore. So this is indeed a function of y, so not x anymore. Okay, so now just simplify this one here. So let's see. We can write 1 over c for alpha minus 1 copy from the numerator. And then you also have a copy of 1 over c from the absolute value. So let me put a constant over there. And let's complete the remaining part. We have the random, we have a y raised to the power of alpha minus 1. And then you have e raised to the power of let's see, how do I want to write this? Okay, let me still keep y over c beta for now. Okay, let me keep it this way. Okay, so I did not change anything from here. And then what else? Okay, so then also the normalized constant stay the same. And then b alpha. Okay. So let me do one more simplification. So 1 over c raised to the power of alpha minus 1, and then multiply by one more copy of 1 over c. So that means you only have one, you have only 1 over c raised to the power of alpha, right? You minus one copy, but you multiply back one more copy. So you only have 1 over c raised to the power of alpha. And that is just the, okay, let me write it down so that it doesn't multiply by that. You will have c raised to the power of negative alpha. Does that make sense? So you minus a copy, but you multiply one more copy, you only have alpha. And I'm going to write the inverse as the negative sign. So you have c raised to the power of negative alpha. And then I'm going to combine this c raised to the power of negative alpha with this beta here. So that will give us the expression y raised to the power of alpha minus 1, e raised to the power of negative y over c beta, and then over the gamma function of a alpha, and then c multiplied by beta together raised to the power of alpha. And now, by looking at this expression, does this expression reminds you any density function for any random, for a distribution? Does that reminds you of any distribution that has a density function that look like this? Sorry? Well, yeah. Sorry, I can see who was talking about. Yeah, it's a gamma distribution, right? Okay, so now we can conclude that, first of all, y, let me indicate, yeah, y, following a gamma distribution. So now the question is, what is the new alpha and beta here? By looking at this expression, or maybe, yeah, I'm not, yeah. So comparing this expression with this expression, what is the alpha for y here? It's still going to be alpha, right? Because this part stay the same. But what is the new beta here? C beta. Yeah. So that for our new random variable y, after we deriving the density function for random variable y, we recognize that this is the density for a gamma distribution, and then with the parameter alpha, but the beta becomes the C multiplied by beta. And this is the distribution for y. Yeah. And also, we kind of like here providing you another methods to recognizing or to answer the question like what is the distribution for something. You can either using the Monge function to calculate the Monge function to recognize the distribution for that new random variable, or you can derive the density function for this new random variable, and then from here recognizing what is the new distribution or random variable here. So this is a gamma distribution. Okay, any question or comments? Okay, I'm not sure if I have time to finish. Okay, I think I have. Okay, if the time does not allow, then I will going to speed up a little bit on the second concept. We only have 20 minutes left, so yeah. So here we talk about the method of transformation for a single variable from x to y. What if we have two or more variables, and this is the result? So let x1 and x2 be random variable with the joint distribution x1, x2. Yeah, it might not looks very obvious, but here when you put down the subscript, it's referring like the capital letter for like the random variables. And then for the input of a function, you can use a lowercase, just as like the input for a function. And this is more referring to a variables, where people usually use capital letter. So just if you want to be like make a distinguish to distinguish the difference between that x1 and x1 and x2 and x2, if you want, yeah. But it not really matter at the here, yeah. But here I'm just referring to the input here. So if the random variable x1 and x2 have this joint probability density function, and then also, so suppose y1, then let me use lowercase then, is a transformation with x1 and x2 with the via the function g1, and then y2 is a transformation x1 x2, and this time we want the joint probability density function for y1, y2, y1 and y2, and then we so we need to define something, but our goal here is that we want the density function for y1, y2, similar to the univariate case where we want a function of y. But this is let's say this is a bivariate case, but you can also extend to more than two random variables. Okay, so our goal is that we want this function here. So we need to define something else. So let x1 be the inverse function with the input y1 and y2. And also x2, let me put a subscript here, h1. And then we also have a h2, which is the inverse function, but with y1 and y2. Okay. So let's say we definitely need to find the inverse function for the G1 and G2. So the idea is similar to in the univariate case. Okay, and we need to further define something else. So let's call this Jacobian, and let's write it J1. And this is the determinant of the following matrix. So I'm going to use, okay. So let me write the terms here, and then I'm going to use a bigger square bracket to cover everything. So here I'm going to define J1. That is equal to the determinant of a 2x2 matrix for a 2x2 variable case. If you have like a p variables, then you need to define a p by p Jacobian matrix and calculate the determinant. But here I'm just going to use the 2x2 case for now. Okay, so the J1 is defined as the derivative H1. So let me just write down everything first. dy1, derivative of the function, inverse function H1, inverse for y1, y2, and then dy2. Okay, so that is the 1, 1 entry and the 1, 2 entry in the matrix. And then for the 2, 1 entry is the derivative of the H2 function inverse with y1 and y2. And then dy1. And then for the 2, 2 entry is the function H2 inverse. You input y1 and y2, and then dy2. So this is a 2x2 matrix. And then you need to evaluate the determinant for this function. Can someone remind me what is the determinant for a 2x2 matrix? So if A, B, C, D, I kind of forget. Is it AD minus BC? Is that the case? I also kind of forget, but I think this is the determinant, right? Yeah. If I remember correctly. Sometimes I forget, but yeah, you can just Google it, but I'm not going to, yeah. I'll Google it later, but you can also just Google it. Yeah, okay. I'll put it down here. Yeah. Okay, so that is the J1. Okay, so let me write down J2. There's another thing you can also calculate, and then you can use either J1 or J2. But let me give you the result for now, which is also the determinant for a 2x2 matrix. The only difference is that this is dg1 x1 x2 over dx1, and then dg1, right? dg1 x1 x2, and then dx2. So similarly, let me speed up a little bit. So this is G2, and then dx1 again, and then dg2 x1 x2, and then dx2. So the only difference for the two Jacobian matrix, the determinant of the Jacobian matrix, is that the J1 is referring that you use the inverse function and then taking the derivative with respect to the new variable, the y's, the one that you want to make the change. And the J2 is referring that you use the original function and then you take the derivative with respect to the original variable, which is the x1 and x2. So that's the only difference. So after we construct all these things here, let me make the final statement here. Then f of y1, y2, function of y1 and y2, is equal to the function of x1, x2, but you need to input the inverse function h1 here, y1, y2. So to replace the x1 here, similar to the univariate case, and then also the h2 inverse y2 here. So you need to plug in the formula for the inverse function, and then here you either multiply by the absolute value for the Jacobian. So don't forget, this is the result of a determinant. So you already get a scalar, and then you take the absolute value. So you either multiply by the absolute value for the J1, and J1 is the determinant of the matrix, or you multiply by the absolute value of J2, but don't forget there's an inverse function here. So it's 1 over the absolute value of the determinant of the Jacobian matrix. So this is the let's say just a conclusion or the result that it can give you the joint probability density function for y1 and y2. Okay, so in 9 minutes, let me give a simple example to demonstrate the case. So I'm going to use example, and let's say y1 following exponential distribution, lambda 1, x2 follow exponential distribution, lambda 2. I hope I can finish this because there are lots of things to calculate. Okay, so let's define the function g. Let's say we define u is g of x1, x2 as x1 plus x2, and then v g2 x1, x2 as x1 minus x2. Okay, so obviously we want the function for u and v here. I'm just not going to write, so let's just write question mark. Well, we want to get that. Okay, so first step, let's find the inverse function. So we need x1 equal to the function y1, y2, x2 equal to the inverse function h2, y1, okay, let me use u and v then. So, well, it's just a notational thing. So y1 is u and y2 is v, and then this is u and v. Okay, so how can we find x1 in terms of u and v only? So the one way you can do is that maybe I'll go over time, but bear with me. So u plus v is x1 plus x2 plus x1 minus x2. So 2x1. So then this gives you x1 equal to u plus v over 2. Okay. And then let's say u minus v, x1 plus x2 minus x1 plus x2. That will give you 2x2. That means h2 is going to be u minus v over 2, right? So this is your function h1 inverse u and v. This is your function h2 inverse u and the v, right? So the function should only input u and v, or y1, y2 in a general case, to give you back the x1. And then the second function only input is u and v, or y1 or y2 in the general case, will give you x2. And that is your your inverse function for g1 and g2. Okay, after we have that, we need the Jacobian. So here I'm going to use J2 because J2 is easier because it's just u plus x1 plus x1 plus x2 and then x1 minus x2. So the first entry, so I'm just going to give the result. So du dx2 and then du dv dv dx2. So I'm going to use the J2, the original function, the original variables, and then determinant. So that should give you the determinant. So u over du dx1 is just 1, right? Here. And then du dx2 is also a 1. dv dx1, 1. dv dx2, negative 1. Determinant. So negative 1 minus negative 1, you have negative 2. But don't forget, you have an absolute value and the inverse later to take care of that. Okay. So again, the determinant is this one here. Determinant of 2x2 matrix. So AD minus BC. So we will have negative 1 minus a negative 1, so negative 2. Okay. Now, I just want to finish in 4 minutes. So u and the v is the x, x1, x2, and then input the two function. I'm just going to use abbreviation for now. J2 absolute value and then inverse. So not the okay, it also makes sense, but so here I'm just going to write absolute value and then take the inverse. Okay. So x and x1, x2 follow exponential distribution. So you will have lambda 1 multiplied by lambda 2 exp negative lambda 1 x. Okay, so here I'm just going to write minus x2, lambda 2 x2. But don't forget, you need to replace the x1 and x2 with the inverse function. So now I'm going to make the change for x1 and x2. So let's see. The inverse function is uv over 2. Okay. So here you should have u plus v over 2. Minus lambda 2 multiplied by x2. And then x2 replaced by u minus v over 2. And then don't forget the Jacobian, negative 2. Take the absolute value and then take the inverse. Okay, so now you should have 1/2 in the front, which is the 1 over positive 2. And then lambda 1, lambda 2, exp negative lambda 1 u plus v over 2 minus a lambda u minus v over 2. Okay, so this, let me write down in text. So this is the joint PDF for u and v. Okay, so as you can see that this expression now only involving u and v. So what we did is that we make the transformation from random variable x1 and x2 to the joint distribution for u and v. And this is the bivariate joint distribution for u and v, the new random variable of interest. Yeah. Okay, so I finished right on time. Okay. Any question or comments? Okay, then I will pause.